Okay, students, I got another great question. Looks like you guys are working on them. That's great. Again, it's from the Harder book here, the University Physics. It's Chapter 3 in the University Physics, but it's one-dimensional motion. It corresponds to the Chapter 2 in our college physics book. But this is the one that often has some calculus or some just harder problems. And so number 81 I want to work with. And so let's just read it here and see what it says. It says something like this. It says a particle at rest leaves the origin with a velocity that increases according to, and I'm going to write this on the screen, v equals 3.2 t. Then, at 5 seconds, the particle's speed begins to decrease according to this equation. So they give us a new equation. So velocity equals 16 minus 1.5 t minus 5. And of course, this really, t minus 5 is the time after 5 seconds. So this is the equation. And notice, well, I'm going to give it away here, but this is going to be a decreasing line, negative, or this is an increasing line. Okay. It then says this decrease continues until 11 seconds. So maybe I should put up here that this was valid for time greater than or equal to 0 and then till 5. And then this would be valid from 5 seconds to 11 seconds. And hopefully they match at 5 seconds. Let's kind of just see here. At 3.2 times 5, this equation, it says it's gone up to 16. And then if you take a look at right here, if you put in 5 seconds, that becomes a 0, and you get a 16. So good, they match. So in other words, it's increasing its speed here. That's a linear with a slope of 3.2, and then it starts to decrease with a slope of 1.2. So the speed increases and decreases like it's saying here, okay? And so that's, excuse me, that's the idea behind this little equation. Now, let me keep reading. Does it have another one here? It says, this decrease continues until 11 seconds. After which, the particle's speed remains a constant at 7. Okay, so v equals a constant 7. And I guess this would be for any time greater than 11. And I suppose we should kind of check. If I put in an 11 minus 5 and multiplied that by 1.5, and then go at 16 minus that 9, I'd get a 7. So again, that's match. So it slows down to 7 and then just keeps that 7. So here it speeds up for the first 5 seconds till it gets to 16. Then it decreases from 16 down to 7, and then it stays at a constant 7. So that's what the problem is describing. I would ask, like any of these problems, and I'll grab my little sheet that you've seen a couple times, is this a constant acceleration problem? And it didn't say it was a constant acceleration problem, but as I mentioned in another solution, the one actually right before this, that if you have a constant acceleration, the velocity will come out linear. So anything that gives you a function for velocity, and so I have functions of velocity, that doesn't look like this, a constant plus a constant raised to a power of 1. Now, I suppose some of these constants could be 0, but you can't have it raised to like a time to a power of 2, or like the problem I was doing, time raised to a power of -1. That would tell you right away it doesn't match this, and it wouldn't be constant acceleration. And so that's what happened back on problem 80. But on this one, if you look, every one is raised to a power of 1. That's raised to a power of 1, so that must be constant acceleration. This here is raised to a power of 1, so it must be constant acceleration. And this one doesn't really look like it's raised to a power of 1, but what they're really saying is you have a constant, that's the 7, and then you're adding 0 acceleration. And that made it very clear when they said the particle remains at a constant speed. And so that would fit a constant acceleration of 0. So this is kind of boring, but it does have a constant acceleration of 0. In fact, I'll even put that in here. This is a constant acceleration of 0. But I do want to then point out, these are constant accelerations. Now, they change, but during the time frame of 0 to 5 seconds, we have a constant acceleration. And I would get that by taking the derivative. So pull the constant out, 3.2, and just take the derivative of t. And so that's just a 1. So I got 3.2 times 1, which is 3.2. So yes, constant acceleration of 3.2. This one is a little harder per se, but it is a constant acceleration. You can see it by taking the derivative. In fact, where was my little sheet I was using for problem number 80? I said, okay, remember that this is how you connect, and I'm doing this right here. I'm taking the derivative of velocity to get acceleration. Okay? And I'm going to take that derivative. The derivative of a constant is 0, so that one goes away. The derivative of this piece, I guess I would pull the constant of negative 1.5 out in front. And then I would take the derivative of those two pieces. And the first piece would be a 1, and then it would be minus the derivative of a constant, that's 0. So this would be 1 minus 0, which is just 1. And then 1 times the negative 1.5 is just negative 1.5. So there you go. I'll just put a little dash by that one and that one. And so maybe I'll even separate the 3 different accelerations. But each of these do have a constant acceleration, and so I really haven't got to the question yet, but I know that I can do these equations. I don't need to necessarily do these, although I did take the derivative, so I could see they were constant accelerations, but they are. So this really isn't a calculus problem. This one is probably hard because I've got 3 different sections. So to apply these constant acceleration ones, I have to break it down into the 3 sections. So I think that's what's going to make this a hard problem. All right, so let's do A. A says, what is the acceleration of the particle as a function of time? Well, I guess I did that already. It's not easy to write that mathematically. We usually do this in what we call a piecewise equation. We're going to say here the acceleration is 3.2 when the time is greater than 0 and less than or equal to 5. After 5 seconds, we're going to say the acceleration is negative 1.5. So that's for time then greater than 5 seconds. Maybe I'll just drop the equal to until 11 seconds. And then for a time greater than 11 seconds, the acceleration is 0. So you have to write it as what we call a piecewise function. If you made a graph of it, it's at acceleration and time. So maybe 3.2 would be right here. And you would do that till you got to 5 seconds. And then it would drop down to a negative value of negative 1.5 until you got to 11 seconds. And then it would just become a 0. So it changes in a quick step. It goes from a positive to a negative to 0. And that's what a graph would look like. So piecewise function. Okay. Then it says, what is the position of the particle at 2 seconds, at 7 seconds, and here's the hard one, at 12 seconds. So the first one's easy. It's just within this range. And so I'm going to go ahead And, well, maybe I don't need a whole neat paper yet. But I am going to then say that since I can use these, and I'm only talking within this range here, let me go ahead and answer their question about what is the particle's position based on time. Okay. And I will put then position is equal to initial position plus the initial velocity times time plus 1/2 the acceleration time squared. And if we kind of define, let's see, do they really say where the position is at 0 time? It says, what is the position of the particle at these? Oh, back at the beginning, it does say the particle at rest leaves the origin with a velocity increasing. All right, so that leaving the origin is the key phrase to say, okay, it's starting with a 0 position. It's even saying its initial velocity is 0. Because again, I'll read it. A particle at rest leaves the origin. This is the at rest, and this is at the origin. Then, of course, we already said the acceleration is 3.2. And they are asking for its position after 2 seconds. So this is the easier of them because it would just be the 1/2 times the 3.2 times the 2 squared and coming up with 6.4 for its position. Now, the harder one is when they say, what is its position when time equals 7 seconds? Ooh. Now, the reason I say ooh is because coming back to our information, the 7 seconds is in this category. And you can't use one equation to go the whole thing because you don't have constant acceleration for the whole thing. But like I've been trying to tell you in class and on another problem, what we can do is we can break it down into pieces and we can say, all right, the ending velocity in the first step becomes the beginning velocity in the second step. And the ending position in the first step becomes the initial position in our second step. So we can still apply these equations, but we just got to be careful with them. Okay, so keeping that in mind, I am going to then apply the same equation to figure out where it is at 7 seconds, but this is kind of the hard thing here. When I ask what's the initial position, I'm in part 2 here saying the initial position where I'm going to use this equation is where it ended after step 1. And step 1 was a whole 5 seconds. Now, if you come back to the math we did it for 2 seconds because it asked for where it was after 2 seconds. But just so it stands out, I'll change colors. If I had done it here for 5 seconds, then this would be telling me its position during the first motion at the end of the 5 seconds as it's ready to begin the second part of the phase of this motion. So let me put a 5 in here and to realize how far it would go during that first speeding up time. And so it's this same equation, 0.5 times 3.2 times 5 squared, and that's a total of 40. So during this first 5 seconds, it goes a total of 40. So during the slowdown part, I'm going to then say that this initial position is 40. And then also, same logic here, is what would be the velocity after 5 seconds for the first part becomes the initial velocity for the second part. So let me put a 5 right here. And also in green to make it stand out, but 3.2 multiplied by 5. 15, that must be a 16. And so after 5 seconds, it's going a speed of 16. Oh, they even said that. That's right. And we already talked about that, 16. So the ending speed here becomes the beginning speed. We could even put the beginning speed of 5, yeah, and got the 16. I guess we talked about that. So I should have remembered that. But maybe it was just as good I did it again. So the initial speed is a 16. Okay. Now, this is where it might get pretty hard. This right here is the time where time equals to 0 would be when it had this position of 40. So the question, which says what is its position after 7 seconds, remember that the first 5 seconds it was doing this motion. So that means I'm only 2 seconds into here. And so really this right here is a 2. Because it is measuring time beyond what we call the initial. And our initial then would be that 5. So that can be a little confusing. But that's the challenge of, I guess, breaking it down into its pieces. Makes me wonder if I would have just been better to integrate it instead of jumping back to these already derived equations. But that's the direction I've gone, so I'll stay that way. Remember, the acceleration is negative 1.5. And, of course, then the time is 2 seconds. So this position would be 40 plus 16 times 2 plus 1/2 sorry, got distracted here. 1/2 times a negative 1.5 times 2 squared. And so this would be position of 69. And so there would be the answer to that one. And that was hard enough, but now finally off to the hardest one. What is its position after 12 seconds? All right, now, again, maybe this would be good to see it, but at 12 seconds, we're talking about this part, where we're going with an acceleration of 0. And we're 1 second in to this movement. So if I write down that equation again, x equals x naught plus initial velocity t plus 1/2 at squared, and I kind of do that same thinking that, okay, the beginning position for step 3 is the ending position for step 2. And that one is this formula that we were calculating it. Now, we did it where we were only 2 seconds into step 2. But if you look here, from 5 to 11 is 6 seconds. So if we wanted to know the position in step 2 after 6 seconds, we would need to change this number here to a 6 and this number to a 6. And we would get, where is it during part 2 after 6 seconds into number 2? Now, fortunately, I'll take advantage of my calculator here and do the shift enter, and then I'll just scroll all the way back, because the 40s then is already there, the 16 is already there. I just got to change that 2 to a 6. And then I have the 1/2, then I have the negative 1.5, and then again, right here, I'll just change that 2 to a 6. And so without typing everything again, I'll just change all the 2 2's to a 6 and hit enter. And writing it in green, that would be 109. So this little formula here tells me where it is after 6 seconds into part 2, which is the end of part 2 and the beginning of part 3. And that's what I wanted to know right here. So I'm going to put the starting position is 109. Now, the starting velocity in part 3 would be the ending velocity in part 2. But as we already said, putting in 11 seconds here gives me a speed of 7. And then, of course, they say it's a 7. And it keeps a 7. So this is pretty easy. It's a 7. And then the time, well, we are only 1 second into part 3. Okay? Because they said at 12 seconds. And so this equation, 0 is when we start part 3. So this is its position. This is its velocity. And of course, the last one here is the easiest of all. It's 0 acceleration. And so then I just have 109 plus 7, which I guess makes 116 meters. And so there would be the position there. Okay. That was definitely a challenging one, too. I can see why it's in this book, and I can see why you guys are asking questions. All right. Hope that helps. Keep up the good work.